and welcome you all to the webinar on emerging trends in the power industry and career opportunities for electrical engineering graduates, organized by the Electrical Engineering Society of University of Moratuwa. On behalf of the EESoc, I warmly welcome our guest speaker, Dr. Dharshana Muthumuni, and all who have joined with us today. As undergraduates who are on the verge of stepping into the power industry, we all should have a vivid account on how the power industry works, emerging trends, and the career opportunities available for us in the future. Nothing can beat the extensive knowledge coming from a well-established personality from the field of interest. So today we have with us Dr. Dharshana Muthumuni, the Managing Director of Power Systems Technology Center of Manitoba Hydro International, to share his ideas, comprehension, and proficiency gathered by working in the industry for nearly 20 years. Having completed his bachelor's in electrical engineering from the University of Moratuwa, Dr. Dharshana has obtained his PhD in 2001. As an undergraduate, he has had a perfect balance in sports and academic work. He has held the positions of the President of the Sports Council and the Captain of the University Cricket team. He has been working with the Power Systems Technology Center of Manitoba Hydro International, the company that develops PSCAD since 2001. Presently, he is the Managing Director at PTC and is responsible for the PSCAD software development and engineering consulting and solutions business areas. Before we get started, we have a couple of reminders to the audience. We kindly request you all to keep your mics on mute throughout the session. And as well, feel free to direct all your questions into the chat box so that we can bring up your questions to our speaker at the end of the session. Now, without further ado, let's move on to what you all have been waiting for. Dr. Dharshana, over to you, sir.
Thank you very much. I'll turn off my video because it's early morning and I'm not in the best of my shapes. Plus, it will help with the connection as well. Thank you very much for giving me the opportunity to talk to you, the class of 2021, I would say, and listen to my thoughts on where the industry is going and the opportunities that you will have in the future because of all the changes that are happening in the industry. So I'll make my presentation. I think most of my presentation, it's a technical discussion on the emerging technologies, the problems, challenges we are facing and we are likely to face over the coming 10, 15 years. And after that technical discussion, let us see what opportunities these new trends open up. I will also talk very briefly based on my experience. I've been in the industry for 20 years. So once you become senior in your senior, and once you have count the years, then you get to interview people like and so on. So I see some of the strengths of CVs, some of the weaknesses in CVs, and when people present themselves for interviews. So I will throw in a few hints based on my experience that I think I hope might be useful. So to get started, I guess you have to make me a presenter. How do I?
Dr. Dharshana, can't you share your presentation now?
Give me a minute. I'm just trying to see.
You can go share screen, that one.
Yes, sorry, yes. Okay, let me know when you can see my screen. Okay.
We can see the presentation now.
Okay. So we are going to talk about emerging trends in the power industry and the opportunities that you're going to have in the future. So this is how the presentation is going to look like. I will talk very briefly. Asini gave an introduction about me, so I won't go into that, but I will give you an introduction. I'll talk very briefly about the work I do, which I hope also will help you to get an understand of how I built my career. Then we will talk about where the world is going, emerging trends. And after that, I will talk about the opportunities, some tips, like I said, on uh, on looking for jobs, both in Sri Lanka and maybe outside. Some of you may be thinking about going for masters and PhDs, further studies. I will talk a little bit about, give you a few hints on how you might want to go about looking for such opportunities, some hints on your CVs, interview skills, and also getting references from your supervisors and professors and so on. So about me, I worked at the university as a lecturer for about 2 years before I went to Canada to do my PhD, which I completed in 2001. And ever since that, 2001, I've been working at this one place. So obviously, I believe that if you like what you do, don't change jobs, stick to the place. And I believe that sticking around in one place or not changing jobs that often gives you the best opportunity to make an impact to that organization and to the industry. I guess in my case, I was lucky that I got a job to develop a product and work with a product like PSCAD that is pretty popular and used worldwide. So my job involves or has involved since 2001 to now, it has involved mathematical modeling. Obviously, when you have a product like PSCAD, you have to keep it up, add new models, take care of the codes in models and so on. So I never I never could get away from what you guys might be studying now, the theories and all the math and all that stuff. So I still have to keep my books. And I love that. Then also as a part of my job, PSCAD, I don't know, some of you may have used it. Some of you may have used MATLAB, software of that nature. So they are used for a wide variety of power system studies. They are used to study the so-called fast transients in power systems, such as, what would happen in your system, what are the voltages and currents that would happen in your system when you have lightning, right? In your high voltage classes, you study the Beverly lattice, that diagram and the calculation. So that's a approximate of estimating lightning induced voltages. You can use PSCAD to do a more accurate analysis. So that's one. It's used to analyze network resonances. You have studied parallel resonance circuits, series resonance circuits in your theory of electricity, right? The reason you study them in year 2 in your undergraduate studies is because these things, right, in a slightly different form maybe, but the theory background is the same. These type of resonances happen in real life and cause issues, right? You don't want to excite parallel and series resonances in your circuit because that's going to cause over voltages, over currents, and damage equipment. So those are studied. HVDC studied. Then in recent times, the response of solar, wind, battery are studied using PSCAD. Obviously, when you study wind energy or wind inverters, the control systems play a big role. What I'm trying to say is the types of things you analyze with PSCAD or the work I do requires a wide range of knowledge on different aspects of power systems, harmonics and power quality. So in my job, I had to know a lot. You might seem, it might seem by looking at this list. Okay, so how do I manage it? Because it's impossible for any one person to remember all these things, remember so much information on so many different things. The simple thing is how one can manage this is just remembering what you study uh, at the university. Because all of these, you just can't remember the details, but they all can be, you don't have to remember a lot if you remember the background that you studied. So don't forget it. Keep all your books handy with you over your career if you want, if you're going to stick to core power system engineering over the next 15, 20 years. Again, like, I mean, now I have certain management and leadership roles. And I think as engineers, you should be looking at that too. Like when engineers manage engineering organizations, I believe that we can make good decisions. I believe that, I mean, there's who's a manager? What can a manager manage unless he knows well and in detail what he's trying to achieve? So that, especially in an engineering setup, comes from having worked in that field, having tackled the issues that you are supposed to manage over a period of time. So when you graduate, you will not go into management or management roles especially, but eventually you will get there, because once you acquire knowledge, experience, you will naturally be in a position to manage things and help younger engineers grow and do the right thing. So when you step in, the new graduates, when you step into the field, respect your supervisors. They have paid their dues over years of time and they will help you grow. I said this already, and this is real. That's why I am emphasizing this. To be successful and to have a fulfilling career, what you learn at the university is going to come to you time and time. It will be the foundation that you will use to make good decisions and find solutions to the challenging technical problems. And also, like, if you don't forget, if you stick to that and build up based on what you study, it will also give you confidence to go out and speak, to not shy away from problems, and to grow your personality. So this is important. So in terms of specifics, in my job, I think electromagnetic transients, like such as lightning and what happens when you switch capacitor banks, or what happens when you open circuit breakers, the so-called TRV, the transient recovery voltage, they are all related to simple response of LRC circuits. All the stuff that you learn under theory of electricity, I'm pretty sure that's the name of the subject still. So that comes in handy all the time. That's really the foundation of electric circuits analysis. Then now, if you are going to talk HVDC, wind, and so on, electrical machines gets into the picture. So have a good grasp of synchronous machines and induction machines. Without having that understanding, it would be difficult for you to make find deep solutions to the problems you will see when you try to connect wind and especially wind and HVDC. Now, power electronics and control system theory, they are going to come in really handy too, especially going into the future. Like until about 5 years ago, I hardly had to deal with control systems because power system was predominantly based on synchronous machines. The only controllers of interest were the exciters of machines. Governors hardly give you problems in terms of stability. So there was not a lot of need for me to, go back to control theory and all that stuff. But now things have changed. It's all about controls when it comes to wind and solar. And obviously, to design machines in general, developer coherently stable in the power system. So overall understanding of power systems is also important. So if you went to the electricity board for your training and rotated around a number of departments like generation, planning, that's important experience and knowledge. So the load flows, transient stability analysis that you study, how they, why they are important in power system planning and design, that information is going to help you become a real good engineer going into the future. And once again, like I said before, like I said, I deal with a lot of areas of power system. Also, things are changing. New technologies, new equipment, new technology are coming into our field on a regular basis nowadays. I mean, battery energy. We didn't have to deal with it. Battery connections almost staple in some parts of the world. Uh, like people are talking about 9-phase induction machines, 9-phase permanent magnet machines, right? So you can't learn them. You can't, at universities, they don't teach you these things because they teach you the fundamentals, the backgrounds of all these designs. So in order to understand the operation of emerging new technology, new things, again, you need to keep what you learned in school very close to you. I also want to mention this point about engineering. In engineering, we are not scientists, right? We don't seek perfection. We want to make things work. So engineering is a big part of engineering, I think, is about, it's my belief, it's about making assumptions and judgment calls, assumptions and judgments. You've got to be able to, let go of things that don't matter, right? Make assumptions and move forward. If you don't have a good understanding of theory, background, and also to some extent experience, past experience gives you confidence, you will not be making those decisions because you're scared, you don't know, you're not confident. So to be a good engineer, to make decisions, you just need to have a sound foundation and build up on that as you learn, get exposed to new things. So let's move on to discuss a little bit about emerging trends in power systems. And what I have to say right at the beginning is you are graduating at a very exciting time, because when I graduated, I mean, looking back, definitely I would say it was a very stagnant field. Not a lot of things were happening. Power systems were predominantly based on synchronous machines, thermal hydropower, like whether it's the machines at Kotmale or Victoria, or machines in India, Canada, doesn't matter. They all had similar, uh, response characteristics. Like all the stability theories that you studied were, predominantly developed to study the stability of synchronous machine-based systems. Over 100 years of operating power systems, people knew what to do, how to design specific, expansions of power systems, people knew they didn't have to do a lot of engineering calculations, a lot of new designs. In fact, they probably didn't even need too many electrical engineers, right? What worked at, Kotmale could be, for most parts, cut and paste at the next generating station or the next substation. They all work the same. It wasn't exciting, but that has changed mostly because of the focus on renewable energy, wind, solar, and these wind, solar, they are connected to the grid, through power electronic converters or inverters. So that has changed the game, so to speak. Large scale integration of wind and solar definitely change the dynamic nature of your power system. The way you operate the power system, where you plan, you'll have to look at it in a different way as opposed to when everything was based on synchronous machines. Controls become very critical, as I will show through. Challenges are, I can say, a future, and I think it's exciting. These things give you a lot of opportunity as well. We also mentioned the technology is changing. Even if you look at probably the wind turbines, like someone's typing something. Is it a question for me or no? Okay, so technology is evolving. For example, even 5-6 years ago, 2 megawatt wind turbines we thought were the cutting edge in technology, right? Now, this year we will have, not this year, next year we will have 14 megawatt wind turbines for offshore wind. So 2 megawatt, 14 megawatt, obviously just look at the size, like the technology to operate them, control them is going to be different. And this is a common trend, like things will evolve. If you look at power electronics, until a few years ago, configurations like this, the 2-level or 3-level VSC, was the topology of choice for high power applications. Now, this is only used, these type of topologies are only used at wind turbine or solar PV inverter levels. MMC technology, modular multi-level technology, is now the default for HVDC connections. And almost on a yearly basis, companies like Siemens, ABB, GE, they are coming up with new topologies inside this MMC concept. So things are changing, like I mentioned many times, and you have to be ready to work in that changing environment. As another example, when you try to connect all of these things together, the new wind turbines, the new inverter topologies, new control concepts that goes with it, and when you try to connect them all together, and in case of an offshore wind farm, connect the turbines through, let us say, 100 kilometer or 150 kilometer undersea cable, you have further challenges. These cables, the cables, because of their L and C characteristics, L's and C's, cable inductance and the cable charging capacitance, the cable itself will throw in resonant conditions, parallel resonant conditions. These electrical resonant conditions interact with the inverter and the inverter controls, and it's a real challenge to retune or find the correct tuning for your controls so that these type of, multi-million, multi-billion-dollar investments will work properly. Okay, so let us take a quick brief look at the global situation. We all know that pretty much every country is focusing on renewable energy, wind, solar, and whatnot. So start with Sri Lanka. We are talking about depending on who you ask, we are talking about 50 to 80% mix of renewables by year 2030. 2030 is not that far. We should start now and work towards definitely throwing the challenges that you will have to solve as engineers entering into the system over the next 5 to 10 to 15 years. Right now, I think the renewable, the power electronic based wind and solar mix in Sri Lanka probably is less than 5%. So that's probably why it's not that these challenges have not popped up in Sri Lanka yet, but they will very soon. In Belgium, for another example, they are committed to reducing their greenhouse gas emissions by 80% from their emissions right now by 2050. So in order to achieve that, they have to make changes starting today. So one of the things they have been planning is to add about 6,000 megawatts of offshore wind, 6,000 megawatts. That's 3 times Sri Lanka offshore wind in a small area, Belgium, right? So these areas of the grid, that area of the grid is very weak. So in order to achieve this target, in order to add about 5 or 6 offshore large-scale wind farms and 2 HVDC links, they have to spend, if engineers don't come and find more cost-effective control system design-based solutions, in order to achieve this connection, they will have to spend probably $1 billion extra on expensive mitigation equipment. You probably don't know this that well yet. So mitigation equipment can be, synchronous condensers, SVCs, and STATCOMs. They are expensive. Of course, engineers will have to design their ratings as well. But the first option that you should look at is, can we retune, redesign the controls to make this work? Because redesigning controls it's free of charge. You already have the controls, you just redesign them, and it all depends on your skills and abilities. Otherwise, you spend $1 billion to make the same condition. Similar situation with in UK. They also have a lot of wind and offshore wind potential, and they are very committed to developing them and increasing their wind and solar potential, solar generation percentages over the coming years. They have started already, and in some parts of England, there's significant percentage of wind penetration. Denmark, again, another country committed to renewable energy, significant percentages already incorporated in or added to the system. And an interesting point here that I thought is worth sharing with you is the fact that at certain times during the year, during the day, they have more wind capacity and more wind generation probably than their load. But yet on some days like that, they still had to import energy from Germany, because you can have the energy, but you don't have the transmission capacity. There are bottlenecks. So that's another challenge. As you as you go high on these renewables, you also have to strengthen your transmission system. So transmission planning gets into the picture. Otherwise, you can't utilize this energy. So in countries like Europe, countries in Europe, interconnections between countries are becoming important. And even in Sri Lanka, if you want to make use of the potential that we have, about 5,000, 6,000 megawatts, I think, including offshore, we don't need that much power for the next, I don't know, 10, 15 years, even probably. So we probably are already, we have to think of, I think we are already thinking of connecting with India, either through HVDC or maybe even, I don't know, AC. It's not that long a connection. Australia, you may have heard about the Australian system, probably, like in some parts of Australia, especially northern Queensland, Victoria, they're operating their grid with more than sometimes 50, 60% of their energy coming from wind and solar. Of course, in 2016, there was a blackout. There was a blackout in South Australia. The interesting thing to note is the government did not change policies. The regulator did not ask to change the way they operate and limit future inclusion of wind and solar. They just went about it. They learned their lessons. They put more engineers to work. They are doing more analysis to avoid such things, but the desire to add more and more wind and solar continues. And it's with a lot of pride that I would point out that the people who lead these changes in South Australia and in Victoria, sorry, in New South Wales, like the head of transmission and transmission planning in those areas are graduates from the University of Moratuwa, like a big deal, okay? Then India, Vietnam, closer to home, they have aggressive plans for wind and renewables. Africa is emerging. So we have just touched this trend. It's going to continue, which means these opportunities are going to be there for the next 15, 20 years. Great for you guys. Okay, so that's the story. Let us pause for a few seconds so that I can take a sip of water. It's pretty early here in the morning, and then we will go into I will show you some practical examples to highlight the challenges we face. So we said the challenges and opportunities are predominantly driven because of wind and solar, which are interfaced to the grid or connected to the grid with those power electronics. So what are the differences? What are the differences that are leading to these new requirements and challenges? For one, synchronous machines are just directly, the winding is directly connected to the grid. There are heavy rotating elements, the rotor, and because of that, the rotating elements and the direct connection to the grid, like we get this benefit that you refer to as inertia. Okay, inertia is, I mean, when let us say Narachole or Kotmale, one of the generating plants, when they trip due to some fault or whatever, if one power plant trips, the generators in every other location on that network will naturally slow down. Right? There are no controls associated. They just slow down. Right? The load generation balance is disturbed, they slow down. In slowing down, the kinetic energy gets kinetic energy in addition to all the power that you push in through the turbines, the hydropower, steam. In addition to that, the slowing down of the machine speed releases the kinetic energy and transfers it back to the grid as electrical energy. That is simply inertia. And that helps, regulates that balance, the disturbed balance between generation and load. So that's a natural buffer to maintain your system's stability. You lose that. When you when you connect generation using power electronics, you just lose that natural inertia, inertial response that you got from synchronous machine, and it is a challenge to deal with that. So now people are talking about synthetic inertia. Synthetic inertia is all about trying to control the inverter and try to make it act as closely as possible to a synchronous machines, at least during disturbances. Okay, and conceptually it's easy. Making it work is challenging, and again, it needs a lot of engineering effort. Number two, second point that I want to highlight is, these generators are connected to your power system, the electric network. So they have to work in a coordinated manner together. Machines, the dynamic devices, should work well when connected to the power system. Same with solar and wind inverters. The performance of solar and PV inverters or the power electronics are influenced by the condition of your network, right? What I mean by the condition of your network, the impedance of the network, both at 50 Hertz, that is what you generally refer to as the fault level of the net system at that particular location, as well as the resonant conditions of your network. The resonant conditions simply are the impedances seen from a particular point. In this case, the point where you are going to connect wind or solar. From that point, looking into the network, the impedances you see at other frequencies. And if you plot them, you will get curves like this, and this is where you identify the so-called parallel resonant points and series resonant points of your network. These resonant points provide more problems or cause more problems when connecting solar and wind than if you were connecting a synchronous machines. Synchronous machines were easier to connect and operate than inverters in terms of maintaining stability, proper control interactions, and so on. So those things, we don't want to go into details, are some points, technical points I want to highlight as to why we are seeing new challenges. One other point to highlight in terms of challenges as a technical point is, both synchronous machines and inverters, they have control systems. Control systems makes their decisions based on measurements coming from the grid, because you are trying to control the power and reactive power or power and the voltage of the grid. So you need to know what's the power level, what's the voltage of the grid at that point as an input. That's the input to your controller. So both of these controls, exciters, governors of synchronous machines, inverters, they need measurements from the grid. In the case of synchronous machines, the measurements, the inputs that you need are the RMS voltage, which is a kind of a steady quantity. Of course, even the RMS voltage would go through oscillations during transients, but it's practically a steady quantity. Power and reactive power flows, again, steady quantities. Okay. Inverters, on the other hand, they also need these steady quantities as inputs, but they also need, very critically, they also need to know the actual instantaneous waveform of voltages and currents, instantaneous values of voltages and currents into their as inputs to their control systems. This is a huge challenge, right? Because, like I said, this is a critical input to the controller, because controller makes the decision on firing the IGBTs of the inverter based on many inputs, but also the instantaneous value of the voltage, right? Okay, but really going to a step further, it makes its decision not based on the instantaneous value, but the instantaneous angle of this voltage, input voltage. The inverter needs to know on a moment by moment basis where you are on the voltage waveform. That is, if you think in terms of angles, the voltage will go from, let us say, 0 to 360, 0 to 360, 0 to 360. This has to be very, very accurately estimated. This is the most critical calculation inside a control system of an inverter. Now, during steady state, this angle will move from 0 to 360, 0 to 360 in a very well-defined pattern. But when the voltage go through a transient, right, that will also change. Because in this case, if you shift the voltage by tripping a line or whatever, that has to be picked by this measuring device. You may have, of course, you have heard of this device. It's the phase lock loop, right? Designing of this phase lock loop is extremely challenging. Like manufacturers like ABB, GE, they probably have hundreds of people working just on improving the performance of this PLL, because if this PLL don't do its job properly, then that's a situation where you will have to invest millions of dollars on adding a SVC or a sink condenser to make this wind farm work. The real fact is, in real life, you don't get sinusoidal voltages all the time. When you have a fault in your system and the system is recovering from a fault, the voltages could look nasty, messy, filled with harmonics like this. But yet, if you want to meet grid codes and stay connected, the so-called fault right-through requirements of wind connections, if the wind farm is to meet those conditions and stay connected, the converter, the control should track this voltage, the angle, the 0 to 360 variation of the fundamental component of this garbage waveform accurately. Otherwise, the controls will mess up, firing won't be as expected, and you will see wind farms trip. So here, making them work together is a challenge. You have to solve that. But if you don't want to go into that and you want to stick with power electronics or controls, you still have work to do, right? Hundreds of engineers, like if you take a company like Vestas or ABB, GE, their R&D team who looks at these type of issues, numbers into thousands or 2000s. Now, even at places like CEB or utilities, in the past, you did not need a lot of engineers to do these connection studies. Now, they don't have in Australia. One of the delays, the challenges is also to find engineers with the right background to do these connection studies. And people are not happy, like the investors are not happy because they just cannot invest their money and connect the wind turbine simply because the utility cannot do the studies fast enough. Like challenging work, engineering work. You just can't assign it to anyone else. You need the engineering strength. So these are all challenges, but they also provide opportunities to you. Just for your information, like you may have heard about fault write-through requirements, power ramp rate requirements in grid codes, right? When you have power curtailment, reactive power, dynamic reactive support requirements that are mandated in grid codes, right? All these requirements are achieved by embedding the math, relevant math, into the control systems. So that's why these control systems are so critical, and they have to be properly designed. These are some control blocks and logic coming from a pretty practical wind or solar inverter setup. Again, if you come to work with my team in Manitoba, you will get to see a lot of these real design details, because they are all designed on PSCAD, and on most times the vendors share this information with us because we help them run their simulations as well. I'm running out of time, right? How much time do we have? 15 minutes? 10?
Maybe that's okay. You may take about 15 minutes.
Sure. I will skip some of these technical discussions. We all get carried away when we get into technical stuff. But maybe I'll just touch on this. Now, see, this is a real life response of a offshore wind farm. If I just focus on this power curve, so before the fault, things were steady. Before the fault, things were steady. And after the fault was cleared, there was a fault, the fault was cleared. If you can look at the voltage, you will note that the fault was cleared. The inverter did ramp up the power at a rate specified through their control system, meeting the grid code requirements, and it seems to have settled. If you look carefully, just after the fault was cleared, there's a power reversal. Like you were operating at 300 megawatts, but before it recovered, the power reversed to about even 200 megawatts. This could have tripped certain elements, and the wind farm may not have stayed connected. This happens because that angle was not properly estimated by the PLL during this transient period. And again, it all boils down to that simple equation. Power is equal to V1, V2 over X sine delta. I'm pretty sure you have studied that equation. Power flow across a transmission element inductor, V1, V2 over X sine delta. That delta was not estimated properly. The VSC, voltage source converter, did not do the right job. I will skip some of these items because I don't think I'll have time. If you are interested, I can come back another day, half an hour, and explain some of these things, but I think it's all good. Then I also listed some practical examples from real life systems to give you an idea of the challenges. I will touch on one or two of them. This example 2 is a situation where you have number of wind and solar or power electronics based connections in a very local area. Let us say in Kandy, or around Kandy, you have a number of wind farms. So in such situations, especially if your if you don't have enough synchronous machines to provide inertias and system strength, these 2 or 3 wind farms can interact in a negative and uncontrolled, unstable manner, causing a phenomena that we refer to as control interactions. Right? If that happens, once again, we need you to come look at the control settings and find a solution. Again, what you learned in school becomes essential. In Australia, when renewable energy levels when the levels go beyond a certain range, they are now experiencing voltage oscillations at around 8 to 10 hertz. This is totally new. Power systems did not encounter this before, about 2 years ago. So first we thought this was just simulations showing a fictitious oscillation, due to mathematical, inaccuracies in modeling. But now we know it is real because these were recorded in the field. So in Australia, in certain provinces, states, they have to curtail solar and wind under certain operating conditions to avoid this oscillation. Because 8 to 10 hertz, even though the magnitude is small, is the visible flicker range. If you allow this, your light bulbs will start flickering. So new challenges, new problems, new challenges. In England, or in general, when you add all these power electronic devices, their control systems can interact with already existing, thermal generation, like what you have at Moratuwa. These power electronics can interact with the thermal generator, mechanical shafts, the big shafts, and destabilize their mechanical resonant characteristics or oscillations. If you allow that, the shafts will actually start cracking and eventually break. That is catastrophic. So again, that's a concern that you have to take care of. So those are some of the challenges. Now, I will now go into the opportunities and let's talk about jobs and so on. I think the 10 or 15 minutes available is enough for me to describe the thoughts and points I had. In terms of expertise, I think going into the future, if we are to maintain our renewable targets globally, we need people with strong power system expertise in terms of planning and operation, right? Even at distribution level, right? Not just at transmission, even at distribution level, things are changing, right? All the rooftop solars, distributed generation, and what we plan in terms of, electric vehicles, electric cars, things would change definitely in how you design and operate distribution circuits as well. So these are expert areas that are going to be important. Power electronics, obviously, control systems, like they fit into any one of these areas or to specific designs of inverter controls and so on. So there'll be a demand for these areas, I'm pretty sure. And if you are interested, the demand for simulations, analysis, mathematics is also increasing. The problems are solved on simulation platforms. So their importance is going to increase. And if you are thinking of what you want to do, think about these as well. Okay, so after graduation, the big deal is to find a job, or some of you may consider doing postgraduate studies. And in my opinion, that's a personal choice, right? So in my personal case, okay, I thought, okay, if I'm going to do a master's or a PhD, I will do it right away. So I worked 2 years at Moratuwa, but I was always my intention was to finish studies, find a job. But that's not the case with all of you. You will be looking at jobs. And I know, like, when you graduate, you apply for, your initial thought will be, oh, I will never find a job, because you didn't get the job at your first interview, or you didn't get called for the first interview. The good news is there are no engineers who didn't get jobs, so you will have a job. The key is to find a job that you will enjoy. I think it's very important to do what you really want to do. So in terms of that, you may already have ideas about what interests you, what excites you in terms of work. So in my case, I was always like I loved machines. So I just tried at every opportunity to stick to that area, like in my research, in my job, and so on. So try to do what you like and what you would enjoy. So in Sri Lanka, I think CB is a great place to work, because utility, transmission, generation company gives you opportunities to learn many things, or get exposed to a wide range of aspects on power systems. Very few other places offer that range. So I think CB is a great place to work. Considering their plans for renewable, it will be an exciting place to work as well. But of course, the danger is you go into these large organizations and sometimes you forget engineering and take care of administration more than the engineering. Okay, so my I don't know, comment is, no matter where you are, like, I mean, don't forget the core engineering part of our job. There's always a place for that if you think hard. Now, I know there are many wind and PV solar developers, consultants, great consulting companies in Sri Lanka. So the opportunities are great. Some of you may eventually, move out of Sri Lanka. I mean, statistically, that's a fact. Statistically, that's the case. So I don't think new graduates, it's a great idea to look for jobs in, Middle East, India, Australia, or England, because when people look to hire from other countries, they are looking for specific experienced people. So if this is your idea initially, you probably won't be that successful. But if that is your plan, you definitely want to think about what the Australian industry is looking for. Are they looking for people with protection expertise, power system planning expertise, wind integration and system study expertise? Have an idea and try to gain expertise on those areas for you to seamlessly and easily fit into these organizations in countries outside of Sri Lanka. Postgraduate studies, my point is, if you are interested in postgraduate studies, it's a personal choice. Go for it, right? Doing a PhD will not make you a better engineer than your friend sitting next to you. That's not the case. You did not do a master's. When you do a PhD, you will learn from people who are acknowledged international experts over those fields, and also doing research, independent research. You will learn, you will gain experience to think independently and to approach problems. So if that is your intention, I say go for it. If you are looking, okay, I think now in Sri Lanka, there's great opportunities to do masters and PhDs. It was not the case during my time. So you are lucky in that sense. If you are looking for placements internationally, like in Canada or Australia, US, Japan, try to look for opportunities by talking to your professors or contacts, because I know like these professors get hundreds of emails per month from people who are interested in doing PhDs and masters and who are looking for funds. So that just sending out CVs, like, I mean, your chances, the probability is low. So talk to people who probably have gone abroad, gone to these universities, have contacts, and they can refer you to the right people, and your chances would be higher. Let us talk a little bit about job applications, interviews, CVs. Like, I mean, you are all very capable people, and you're confident that you can do the job that you are applying for. So give yourself the best chance. The people who are people who are hiring you, they don't know you yet. Your way to introduce yourself is through your CV. So make sure that you have a good CV. Personally, I don't fancy CVs with a lot of color and designs and all that. I say keep the appearance also simple, but mostly the content. Be compact and precise. I say, like, if I'm reviewing a CV, I try to look at hints to convince myself that this person is a strong technical person, has strong technical skills. So try to highlight that, and also try to be specific when you're describing your past experience. In your case, you don't have past experience, you are new graduates, so it would be your project work and also your industrial training. So in your CVs, maybe you can list this. Example, I'm taking 2 examples. Example 1, you may say 3 months training at the Victoria power plant. These are the stuff that you did. Generator maintenance, CT replacement, generator testing. Second example, I have seen this myself. Someone will say, oh, developed fuzzy neuro control system based on bifurcation theory for a wind farm. It sounds really fancy. It means nothing to me. So I strongly say avoid these type of things. Example number 1, it's okay, but you're not doing yourself justice. Example 2, it means nothing to me. So what I say is be specific, right? For example, under example 2, a better way, in my opinion, to demonstrate what you did was to say, okay, I developed this fancy controller for a wind turbine, but explain why, right? For example, say, connecting large-scale wind farms to weak grid locations is a known challenge. We know that. Designs based on conventional control concepts have failed to address these oscillation issues of offshore wind farms connected via long cables or whatever. Just be specific. Tell the person who's reading this that you know what you're talking about and you know why you are doing what you are doing in developing this. And then say, okay, because of this, a decision based on and design based on this fancy control approach was investigated. You did that. And then you can say the applicability or the validity of what you did was demonstrated through, let us say, simulations. And you can put in a word like MATLAB, so that the person who's reading your CV knows that, oh, this guy knows a little bit about MATLAB and simulations, and we need that in our organization. This is a high, this is a good candidate, right? I hope you get the point. Like the CV, whether you are applying for jobs or research position, it's important. So that's why I spent probably 10-15 minutes last night putting up these true examples for your, hopefully for your benefit. Okay, so if you are going for postgraduate studies, I discussed this. Try to go through contacts as much as possible. Like you can talk to me as well. There are a lot of people who took off from University of Moratuwa, did PhDs, did well, did great. So when someone from your university had done well in the past, that that professor, that supervisor would be keen to listen to what he says and that person's recommendations. So try to go through contacts. Again, finally, at interviews, what I say is be yourself. Don't just talk, just be your normal self. Let your personality come through, right? But also highlight of your technical skills. That is important. But most, all of you have technical skills. So when I'm interviewing, we're 10 of you, in terms of technical skills, the projects that you are describing to me, you would all look the same. Maybe your grades can be a differentiating factor. But so aside of that, generally people will try to read between lines to see if you would be a good fit, if you will see the bigger picture, if your approach makes common sense. Common sense is a big deal, right? So try to highlight that, try to show that you're not someone who will get stuck in details and never get the job finished off, done. That you can go beyond details, make assumptions, see the bigger need and the role, and finish a job. Try to highlight that when you answer questions at interviews. And finally, you guys are in a great position, you are going into a world where your profession is going to throw in great opportunities, hopefully bigger salaries as well. But I mean, in my opinion, way to fulfillment, success is a hard work. That's really what it is. And you have to enjoy what you do, because the job you do is really a huge part of your life. You spend 10 hours a day on that. So you have to enjoy what you do, keep smiling, have fun, and all of you will do very well in life. Good luck. Thank you, and I do hope I didn't waste all of your time. That some stuff I mentioned, pointed out, would be useful. And
thank you so much.
Thank you.
Thank you so much, sir, for the enlightening session. We have received a few questions from the audience. May I read them to you, sir?
Okay.
First one, sir, can't we have inverters in operation below its rated output and make it automatically loaded when there is a sudden frequency fluctuation in the system, just like inertia of synchronous machine helps?
Yes, you can do that. So that is, now we are getting technical or too technical, but yes, you can do that. So that is generally what we would refer to as frequency sensitive modes of operation, or synthetic inertia. Okay, if we are to call it synthetic inertia, what we are trying to do then is trying to mimic very closely the response of a synchronous machine. So what do we need to do then? Because what we said was synchronous machines, when one generator trips, all other generators will slow down naturally without any controls or any help. It's just a natural response, right? If you were to mimic that, through an inverter, if we were to mimic that through an inverter, first you have to detect that your frequency has dropped, correct? Like inverter, the control, like you just said, like you have to change, you have to know that the frequency has dropped, and you have to change the power reference point, or you have to increase the power reference point. So that's the difference. That detection that something has changed, the frequency has changed, takes time. It's not an instantaneous natural response. You still have to figure that, the measuring system will have to figure it out. So there is a delay. And if you can keep that delay as short as possible, maybe a few cycles, then the synthetic inertia would help your system stability. In some other cases, you probably really need the support from a synchronous machine, because that delay may be the difference between stability and instability. Did I answer your question?
Yes, sir. Thank you.
Okay.
Next question. Sir, is postgraduate studies necessary to be employed overseas?
Not really. Like, I mean, no, like, I mean, there are so many people, like, you need specific experience. If all you did was administrative work in your previous job, then it would be very difficult to, convince employers to hire you, because there are so many who would graduate from local universities of that area in that country, who they would prefer to hire over you. So specific experience is necessary for some specific jobs. Masters and PhDs is probably an advantage. When I hire, first thing I look at is what you did in your undergraduate. And I'm not saying that you have to have gotten all A's or anything, but a general trend that shows that you have paid attention, and also your experience. So that's why I highlighted those two examples in the CV. Tell the prospective employer what you did in a way that he can understand how your experience can benefit that organization.
Next, sir, can you please explain how artificial intelligence affect in power sector industry? Is it going to challenge power sector jobs?
Oof, I never thought about it. I have not seen. There's no reason for me to think that it will challenge our jobs or anything like that, if that was the question. Artificial intelligence is discussed as a potential application in power systems. Maybe I don't really have the background to give you a good answer, but I really don't think it will be a big concern.
Thank you, sir. We have covered all the questions in the chat box. And are there any other questions from the audience?
Hi, Dharshana, Androjepal.
Hey,
Yeah.
sir, how are you, sir?
Yeah. Nice to see you. Yeah. I listened
Not bad.
Yeah, I had a
Dealing
lecture
with
on semester 6 from 4:30 p.m. to 6:30 p.m. and I finished it in time to join you. So, few questions.
Thank you.
How are you doing?
Not bad.
Okay.
Not being able to travel and come home.
I know.
It's not the best option, best situation, but life is such.
We all face that, yes. A few questions. I have 3 questions really. One question is that you are emphasizing on offshore wind. Is that because of the cable or the size? Because the offshore wind comes in bigger scale, say more than 7 megawatts in or 5 megawatts in unit size, and then the cable size, very invariably connected through a cable to the grid. but the onshore doesn't have that component. The onshore is differently also smaller in scale. Is that the scale and the cable that matters most?
It's the cable. So like these cables, the long cables, they introduce a network resonant, parallel resonant point, generally in the third, fourth harmonic region. So when you go through a transience, when you go through a disturbance, the voltages and currents would have components of that transience, and the PLL output gets modulated, right? So the controls gets into all sorts of oscillatory behavior, like you have to have filters. I mean, you can't have filters in the system because that's going to be costly. So you have to put filters in your control parts. When you put filters in the control parts, it makes the controllers actually slow and rugged against any other. So those are the challenges. So yeah.
Okay. Now the second question is, now you are talking about this economic challenges faced by wind, solar, and so on. But the countries like us, where the per capita GDP is less than $4,000, we are struggling to keep up our economics, and poor people are very poor and struggling, and we are living in a country like that. So that for all these challenges of going for renewable energy and higher percentages and and we are being a very low emitting country. Our emission per annum, 1 ton per person per annum. Compare it to any country, we are in the rock bottom. Right. And still our generation, if you look at the past generation, our renewable generation has been on average about 50% electricity. Yeah. 50% electricity. So we have been doing pretty well. That therefore, so in our future planning, I presume that even your advice should be that, we should go, our decision making should be based on economics also, and more than, and the technicalities as well as the economics as well.
Yeah. So as engineers, we are there to solve the technical problems, right? So the bigger decision of whether to invest in solar, wind, or thermal comes predominantly, of course, policy. Like if you want, like you just said that our emission levels are low, so emission is not a problem. So then the investment, the planning, long-term planning decision is purely based on economic reasons, right? You consider the total cost of a power system operation over a period of 10 to 15 years by doing a long-term transmission generation planning study. If that study comes out that, if those studies show that out of the generation resource, the generation mix that you have, all your wind resources, solar potential, the money that you have to spend on, coal or gas, considering all that, if the mathematical optimization process that you follow in a long-term generation planning, if it shows that going into wind and solar is economical over the others, then you go for that. Otherwise, you do. So you are absolutely right. The big decision should be based on the cost benefit. Then, if that is the case, what I'm saying is, if that is the case, technology, stability, things like stability should not be a deterrent to implement those plans. The engineers are there to deal with these problems. What I'm saying is, the cost of operating a power system over 30 years goes into multiple billions of dollars. Adding a synchronous condenser to solve technical stability issues is $10 million. It's nothing. So I totally agree with you, but it has to be done. That plan has to be done in the scientific industry, following industry practices and standards.
Okay. My short third question is that, that also I have been teaching students of making CVs, and you also talk about that. But I met last couple of years, not this year, because this year, January, I traveled a little, but afterwards, no traveling. I have been traveling to China many times, and I met many undergraduates from China.
Okay.
Right? But when I met them, when I asked them, I normally ask them the question after passing on, what you want to do. Normally their question is, so I want to start my business, and I want to do this, I want to start this, I want to sell this. Entrepreneurship. They never, Chinese undergraduates, they will never take. I have met many universities and many industrial places, undergraduates and graduates also, and they never talked about making a CV. They talk about to do something themselves and to make a entrepreneurship and making a new business, right? Unfortunately, in Sri Lanka, now we have a career guidance unit in university. So main purpose is to teach students to make a CV, impressive CV, right? So we never inculcate on students to produce something, do something alone, be an entrepreneur, and do impress and all that. So I think there is something wrong. I think even myself, I see that I have been there for many years now. I am as old as you in the field. So I think there's something wrong in the country. Entrepreneurship we have not been promoting. So I think in the future at least, now we have, I think we are about 100 students, 100 newcomers are listening to us. I think we should inculcate the culture that, of course they can do a job, but at least some of them can start a job of themselves, creating jobs and be entrepreneur and expanding their knowledge and be a, standing pillar in that sector.
No, absolutely. I mean, people should be encouraged and given the directions or that mentality that you should think think like that. Not all of the class will become business owners or whatever, but if you train them, the people with that right skill will go in that direction. And also leadership, like, I mean, at some point we should be ready to take leadership roles. Otherwise we will always complain that, oh, like, I mean, a non-engineer is leading an engineering organization. I think it's our fault because we get sometimes too stuck in in details, doesn't really appreciate the big picture, and let people who don't have that background and the real qualification to lead us. So leadership. So that's why I think the EESoc, these things are very important. They teach also leadership to young people.
Okay, I leave there. Thank you, Dharshana. Take care, and my regards to your family. Take care.
Thank you, and looking forward to meeting you, and all of you, soon, hopefully.
Okay. Okay.
Thank you.
Thank you so much, sir. Is there any other question?
One short question. Dr. Dharshana, thank you very much. I was listening to your presentation from the beginning. It's really interesting. So this one small thing, just to get some idea from you. So you were referring this modular multi-level inverter. So what is the widely used number of levels as far as this wind and large scale wind farms are concerned?
Oh, so before I answer your question, I didn't know you were there. I think I have had a successful or fulfilling career. And if I want to, I thank everyone, Dr. Lucas, Dr. Vijay Tunga. But if I want to thank one person who just motivated me and pick one person, that's you. And I just want to once again acknowledge that and thank you for all those, the way you taught machines, right? It just was amazing, and I just benefited immensely, and I hope this class did too. So thank you.
Thank you.
So in terms of MMC, and I still hope that you will come visit us, and
that's what I'm planning. Surely, I'm looking forward to that.
I don't think you will ever do that because I have been trying for the past 10 years, but that's okay. So MMC, So wind and solar, they predominantly use 2-level or sometimes 3-level or a minor variant of that. So they don't go into the MMC. So STATCOMs are now again going into MMC technology. HVDC is 100% MMC.
MMC.
So in general, if I'm wrong, I will go back to I'll go back and email you the correct answer. But off of my head, we are talking like few tens, maybe hundreds in that range of levels, as opposed to what we thought initially that, okay, we might be going into 500s, thousands. I think we are talking tens, and it definitely depends on the voltage level as well. I'll correct myself if I'm wrong, sir.
Sure. Thank you, Dharshana.
Thank you.
It's nice to see you. So give my regards to your family also, Dharshana.
I will. Yes, I will. Absolutely.
Thank you so much, sir. Are there any other questions from the audience? Seems like we have covered all the questions. I would now like to invite Dr. Tushara Ratnayakar, the president of EESoc, to make a thanking note.
Dr. Dharshana Muthumuni, thank you very much for the valuable talk today. So I am sure our students are so blessed to hear you with that much of industrial exposure and broad knowledge. So accept my heartiest gratitude on behalf of EESoc for kindly accepting our invitation and delivering such a valuable talk. So targeting mainly our students of the Department of Electrical Engineering. We expect your support in our future activities as well. Thank you very much, Dr. Dharshana. And also thank you, Professor Vijay Pala, for letting us his lecture time for this session. And at last but not least, I would like to thank the audience who joined us today. We had a very good audience today, more than 130. Some of our staff members also joined. So thank you very much. So because without you, this would not be a useful session. And your lovely participation by asking questions is highly appreciated. So thank you and stay safe, everyone. Okay, we will wind up the session here.
Thank you very much. It's always great to talk to all of you at university, and I want to also thank my friend, Dr. Dharshana, who probably tossed my name and invited me. So thank you very much, everyone. And yeah, like if you need any help or like technical insights, question, just ask me. If you want PSCAD license, definitely ask me. I can definitely provide that. Thank you.
Thank you very much. Thank you.
That's I will call you. Okay.
Sure. Thanks. See you.
Thanks. Okay. Bye.
Bye.
Thank you very much, sir.
Bye.